This is part 9 of the series, An Introduction to the Derivative, and in this part I just wanted to work out some extra problems just to give us a little bit extra practice. So the first problem I want to work out is I want to take the second derivative of this function. The second derivative is denoted as d squared y dx squared. That is the second derivative of y with respect to x. So here this is an implicitly defined function, and the first step is to take the first derivative. So let's go ahead and do that. So this is 2x plus 2y y prime equals 0. Now we have to solve this for y prime. So we have 2y y prime equals negative 2x, and y prime equals negative 2x over 2y. Simplifying, we have y prime equals negative x over y. And now we'll take the second derivative. And the second derivative we can denote y double prime equals, in this case we're going to have to use the quotient rule. And in addition we're going to use the constant multiple rule and pull out that negative sign. So that's negative low d high, which is just 1, minus high d low, which is y prime, all over low squared. Now let's simplify this. We have negative y plus x y prime over y squared, and that's equal to y double prime. Now at this point we have a bit of a sticky wicket here. We have a y prime term in here, but not to worry, we have y prime in terms of x and y. So we're going to substitute this expression in for y prime over here. So we have y double prime equals negative y plus x times this expression, negative x over y, all over y squared. So continuing on, we have y double prime equals negative y. This times this gives us negative x squared over y, all over y squared. And we have y double prime equals this times this, which is negative y squared, minus this times this, x squared over y, all over y squared. And now we're going to alter this because this is y squared over 1. So we're going to change this out. So we have y double prime equals negative y squared minus x squared, all over y to the third. And as a final touch here, we can factor out a negative 1 out of the numerator. So we have negative y squared plus x squared, all over y to the third. That wasn't really necessary, but just for completion's sake. So there is an example of the second derivative. So let's go ahead and revisit some of our trig functions, and we have y equals sine of 2x. So here we have an explicitly defined function, but we're going to have to use the chain rule because we have an outside function, sine of some value, plus an inside function. Oops. So let's go ahead and differentiate this. Y prime equals, take the derivative of the outside piece, derivative of sine is cosine, with the inside piece intact, times the derivative of the inside piece, 2, which equals 2 cos 2x. Now please don't make the mistake of thinking that this is sine times 2x. Some people make that mistake with all these gyrations going on. This is simply the input to this function. These are inextricably linked at this point. So this is not a multiplication, so you can't take the derivative of cosine. This isn't the product rule or anything like that where we say the derivative of sine times the derivative of 2x. That's not how it works. So this is the final result of the derivative of this function. Let's try another one that's similar. So here we have y equals cos of x minus 1. So here y prime equals, the derivative of cosine is negative sine times, with the inside piece intact, times the derivative of the inside piece. Well, the derivative of the inside piece is simply 1. So this equals negative sine x minus 1. Now, I wanted to work a couple of examples where the interpretation of parenthesization is critical to the solution of the problem. For this one, we have y equals cos 3x squared. Now, the only effective way to interpret this problem is that the parentheses belong here. Any other interpretation would be contrary to convention. So given that this is the correct interpretation, let's go ahead and take the derivative. So we have y prime equals, derivative of cosine is negative sine, and we have the inside piece intact, times the derivative of the inside piece, the chain rule. 2 times 3 is 6x. So simplifying this, we have negative 6x sine 3x squared. So here we have a similar problem with a different positioning of the parentheses. Now, at first, you may be tempted to think that this is the product rule until you realize that the cosine of 3 is simply a constant. So we're going to utilize the constant multiple rule. So y prime here is equal to, rewrite the cos 3, and we're just going to differentiate this with the power rule, 2x. So just to make it a little prettier, this equals 2x cos 3. And that's the end of that one. Now let's look at something that's even closer. Now, when looking at this problem, you might be tempted to think this is saying cos squared of 3x, or cosine of 3x, the entire quantity squared. But just keep in mind your rules for parenthesization and exponents. This square applies to the thing immediately to its left, so this is the cosine of 3x squared, 3x quantity squared. So with that interpretation, before I differentiate, I want to rewrite this. So this is going to be cosine of 3 squared is 9, x squared is x squared. Now we have something a little easier to differentiate. So y prime equals, derivative of cosine is negative sine. Keep the inside piece intact. and then we differentiate the inside piece, which is 18x. So the result would be negative 18x sine 9x squared. Now let's look at yet another slight variation on the theme. Here we have cos squared 3x. Now the interpretation of this, when you see the square next to the trig function, the interpretation has to be cos 3x squared. So now given that piece, our derivative is 2 times cos 3x times the derivative of the inside piece, which is negative sine 3x times the derivative of the inside piece again, which is 3. So this is a doubly nested chain rule. So here we have 3 times 2 times negative 1, which gives us negative 6 times cosine 3x sine 3x. Well, I hope you found this series useful and helpful. If you wish to learn more, please check out the other videos, the proofs that I have, and look for the next series on applying the derivative. So I hope to talk to you in the next session.